Today, I'm going to talk about how magnets work. There are two basic types of magnet: permanent magnets, which are the type used on fridges, and electromagnets, which are used for more industrial purposes. Before I get to magnets, however, I want to discuss the electric force, because the electric force and magnetic force are really the exact same force. I'll explain how that works in a bit, but first, electricity. The electric force is an interaction between charged particles via an electric field. Each particle creates an electric field which interacts with each other charged particle. There are two types of charge: negative and positive. Oppositely charged particles attract, while like charges repel. The more charge a particle has, the stronger the electric force on it. Likewise, a particle with no charge on it doesn't interact with an electric field at all, and thus experiences no electric force. Furthermore, you can obtain zero charge by combining an equal number of negatively and positively charged particles. Think of atoms. They have an equal amount of positive protons and negative electrons, and thus have a neutral charge. Now, there is a bit more to the electric force than this, but it should be enough to understand the following discussion on magnetism. Magnetism, as it is normally described, is very similar to the electric force. A moving charged particle will create a magnetic field that other moving charged particles will interact with. The higher the charge, or the faster the particle is moving, the stronger the magnetic force on them. This is the underlying basis of magnetism. Now, to explain where this comes from, I'm going to move on to the electromagnet. At its base, an electromagnet is just a wire with current running through it. Since current is just a bunch of moving charged particles, they create a magnetic field. You can find the direction of this magnetic field using the right-hand rule. If you stick your right thumb in the direction of the current and wrap your other fingers around the wire, your other fingers will point in the direction of the magnetic field. So, if the current in a wire here is moving to the right, then the magnetic field below the wire will be into the screen, as represented by crosses, while that above the wire will be out of the screen, as represented by dots. Now, the magnetic field from a single wire is actually quite weak, but we can strengthen it by combining a bunch of wires, all with current running through them. One of the best ways to make a strong magnetic field is to wrap one long wire in a circle a bunch of times. This creates a solenoid, and from using the right-hand rule, we can see that it creates a very strong internal magnetic field. The external magnetic field is quite a bit weaker, because the field from opposite sides of the solenoid cancel out, but inside it is strong. The direction of the magnetic field depends on the direction of the current, but in this case, we will say that the current runs counterclockwise, and so the magnetic field is out of the screen. A lot of times, a piece of metal is put in the center of the solenoid. This both gives the wire something to wrap around and helps direct and strengthen the magnetic field, so it can be used to interact with other things. We can also wrap the solenoid itself in a circle. This creates a toroid. The magnetic field is still very strong in the center of the wrapped solenoid. Such a device was hypothesized to be able to contain the plasma for fusion reactions. Such a device has not been able to work yet, but the idea remains. A big advantage of electromagnets in general is that they are entirely dependent on current running through them. If you cut off the current, the magnetic field stops. This controllable magnetic field makes them very useful in situations where controlling a magnetic field might be needed, such as with an MRI. Now, so far, I've described electromagnets and their uses, but I haven't really touched on the cause of magnetism. Well, for that, we're going to need to be familiar with length contraction. In short, length contraction is the phenomenon where objects moving relative to you appear shorter or contracted. For a more in-depth explanation, as well as its cause, I recommend you watch my video on length contraction. The best way I can explain magnetism is by going back to the single-wire electromagnet. For this wire, let's say we have a current running to the left. Now, current is actually a measure of the flow of positively charged particles. And since negatively charged electrons are the ones actually moving, the electrons are flowing to the right. As one electron flows past part of the wire, that part of the wire has a brief positive charge from the protons. This then attracts another electron, causing it to flow to the right. This process repeats throughout the entire wire, dragging electrons along at a constant rate. This ensures that there is an equal number of negative electrons and positive protons at any point in the wire. If it ever becomes unequal, electrons will move to balance it out. Nature likes balance. Since the wire is neutral, if we put a stationary, positive particle next to the wire, it will just sit there, since there is nothing for it to be attracted to. This changes if the positive particle starts moving. For our purposes, we will say that it goes to the right. Now, from the reference frame of the wire, we say that the particle interacts with the magnetic field. But to understand what is really happening, we switch to a different reference frame, one following the positive particle. So, in this new reference frame, the particle is stationary. The electrons are also now moving quite a bit slower than they were, and the protons are now moving to the left. Since the protons are now moving, they experience length contraction, while the slower moving electrons experience the opposite, length expansion. This results in more protons in the wire than electrons. So, from the frame of reference of the moving positive particle, the wire becomes positively charged. As such, the particle experiences an electrically repulsive force. So magnetism is just a simpler way to describe the electric force under the influence of special relativity. Now, at the everyday speeds the particle is traveling at, effects of relativity are nearly negligible. So how can length contraction have an effect? Well, nearly negligible isn't completely negligible. Length contraction creates a noticeable effect because protons and electrons are so small. So if the length of protons only contracts a bit, it still allows a bunch more protons to enter the wire, giving it a positive charge. Now, the positive particle doesn't have to be moving to the right. It could move in any direction. You can determine the direction of the magnetic force, if one is present at all, by looking at the particle reference frame and determining if more protons or electrons accumulate, or if the wire experiences length contraction at all. These effects can all be summarized with another right-hand rule. If you stick your thumb in the direction of the moving positive particle, and the other four fingers in the direction of the magnetic field, your palm points in the direction of the force. If a negative particle is the one that's moving, you use your left hand. The key takeaway from this, though, is that the magnetic force is just the electric force when special relativity is involved. Now that I've discussed electromagnets and the ultimate source of magnetism itself, we can move on to permanent magnets. Now, magnetism requires moving charged particles. So what are the moving charged particles in normal materials? Electrons, although they aren't really moving. Aside from other inherent properties of matter, such as mass and charge, particles also have an intrinsic magnetic moment. This means that particles just naturally have a magnetic field. So while electrons don't need to be moving to create it, they all create a magnetic field. We don't really know why this is the case, but it is. Now, when electrons come together in atoms, it is possible for the intrinsic magnetism of each of the electrons to cancel out. This happens for atoms filled with electrons. But if an atom only has a half-filled outer shell, then all the magnetic fields of the electrons point in the same direction. Other magnetic fields can be created from the electrons themselves moving and from protons, but these effects are significantly smaller than the inherent magnetism of electrons, so they are often neglected. Now, while certain atoms have net magnetic fields, there is no guarantee that the material will be magnetic. For the material to be magnetic, all of the atoms in a crystal have to be aligned. This only occurs for a handful of these half-filled atoms. Any of these materials with aligned atoms in their crystals have the possibility of being magnetic, and they will all be attracted to actual magnets. Iron is such an example. However, only those materials which have aligned crystals will actually be magnetic. In simplified terms, a crystal is just a subset of a larger material. If the magnetic fields of all the crystals are aligned, then the material will be magnetic and create a magnetic field. At this point, I've pretty thoroughly described how magnetism is created. But how does that attract other magnets? Well, the short answer is because the magnetic field lines created by magnets are not straight. Let's take a look at our solenoid from earlier, tipped on its side. Current is going into the screen on the top and out of the screen on the bottom. This creates a magnetic field going toward the left. Due to the way moving charges create magnetic fields, the field is curved at both ends of the solenoid. We can actually compare this to a permanent bar magnet. Maybe I should have mentioned this earlier, but magnets have two poles. A north, where positive magnetic fields come out, and a south, where magnetic fields go in. Comparing the bar magnet to the solenoid would have the north end pointing left, with the south end to the right. From this comparison, we see that permanent magnets can be interpreted as circling currents. Now, let's say we bring another bar magnet from the right close to the solenoid, north end pointing left. If we interpret the bar magnet as being made of circling currents, we can see, from the right-hand rule, that the magnetic force is perpendicular to the magnetic fields. If we split the force into its components, we find that the up and down magnetic components cancel, but the components pointing to the right add together. This causes the south pole of a magnet to be attracted to the north. If we flip our bar magnet around, the force now points in the opposite perpendicular direction. This means that two north poles, and from the same logic two south poles, repel each other. Now, we've discussed how magnets attract other magnets, but how do they attract random bits of metal, such as iron? When a magnetic field shows up near a possibly magnetic material, the crystals of the material align with the external magnetic field. This is actually how permanent magnets are made in the first place. They are subjected to the magnetic field of the Earth, causing their crystals to align permanently. With the random metal aligning parallel to the magnetic field, the metal will always have an opposite pole towards the magnet. So if the north end is brought near a paperclip, the paperclip will have the south end nearby, and vice versa if the south pole of the magnet is brought near. With the random bit of metal now magnetized, the process I described previously takes over, and the magnet and metal attract. And that is the answer to magnets. How do they work? Moving charged particles create magnetic fields, which are electric fields with relativity taken into account. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.